Okay, and welcome to our second lecture in Unit 4. We're going to continue from our discussion of thermodynamics by heading into state functions. So, regarding state functions, the State of the Union is an address given by the President to Congress every year. Well, not necessarily every year. It's mandated by the Constitution that he'll inform or report to the Congress from time to time, so on. It doesn't have to be in person. It doesn't have to be a big political speech. That's just, politics. You could just send him a copy of Newsweek if you wanted. But the State of the Union is just a report on how things are in the country as a whole. The state of the system is how things are in the system. You're talking about any measurable quality or quantity of the system. You could talk about the charge, you could talk about the number of particles, the temperature, the volume, the pressure, any kind of energy, gravitational, chemical, electrostatic, all these different things. Anything you can measure, really. It can be part of the state of the system. So a state function is any property of the system that only depends on the state of the system. It could be temperature, pressure, volume, any number of things that only depend on where the system is and not how it got there. So let's consider an example. First, temperature. The temperature of the system is going to be independent of the path you take to get there. So let's say you measure it over time. Just follow the temperature as it changes over time. It's going to start at a low point and then heat up, or it could start at a high point and cool down. It could go down, then up, then back down again. It doesn't really matter too much, what happened before. The temperature of the system is what it is. You could cool it down, then heat it up. You could heat it up, then cool it down. The temperature is going to be 30 degrees either way. The path doesn't matter. In a similar vein, we have volume and pressure, the size of the system and how hard the system is pushing on its surroundings. They only depend on where you are and not how you got there. They are state functions, and they show up all the time in thermodynamics. But we can make a useful distinction between path-dependent functions and state functions by looking at displacement versus the distance you have traveled. Remember, displacement just means how far apart 2 points are. Distance traveled means the distance along the path. So if you have just a simple graph, for example, you consider that you are located at the origin, the center of the graph here, and you have another point located over here in the first quadrant. The displacement is how far apart those 2 points are. No matter what, the distance between those points is always going to be the same. Call it 5 miles. But you can travel different paths to get between those points. The shortest possible distance, of course, is 5 miles directly northeast. But you could also travel to the east 4 miles and then to the north 3 miles, giving you a total of 7 miles. Getting to the same point. Or you could travel southeast, then north, and northeast, then east by northeast to half east, for a total of 12. It's kind of ridiculous. Maybe you have some errands to run, but you could still do that. So displacement is a state function. It doesn't care about the path you travel to get where you are. You are wherever you are. But the distance you travel is not a state function. It is a path-dependent function. You can think of that as being the opposite of a state function, where it depends on what path you take to get where you're going. A path-dependent versus a state function. So, displacement is one example of a state function. Other state functions would be things like temperature, volume, pressure. They're all path-independent. They don't care how you get where you are. They just are what they are. But other things are path-dependent functions, and you have to keep those differences in mind. So work is one example of a path-dependent function, and another one is heat. Keep in mind, these are both path-dependent functions. These are physics terms, for work and heat. We've already discussed heat. We'll be getting into work more in a bit. But you can't treat those as state functions. But pressure, volume, temperature, and energy are all state functions. Now let's go ahead and talk about the internal energy of a system and the first law of thermodynamics. The internal energy of a system, or U, as you can see over here, the internal energy of a system is every single bit of energy inside the system. This includes thermal energy, nuclear energy, chemical potential energy, everything. However, U, the internal energy, cannot be measured. Not directly, not indirectly. It's simply not possible. There's just too many things that cannot be known. It's not practical. It's not even hypothetically possible. It's just not something you can do. That said, if you're careful, you can measure delta U, the change in internal energy of the system. You have to set the system up carefully. You have to control these things, but it's something that can be measured. So final minus initial, delta U, can be measured. For example, you warm up a cup of coffee. You add heat to the system, you're increasing the internal energy of the system. Regardless of anything else, hold everything else constant, you've changed the heat of the cup of coffee. You've changed the internal energy of the cup of coffee. So when you combine two hydrogen molecules and one oxygen molecule to make water, the whole system has to have the same total energy. But you know that the water molecule has lower chemical potential energy because some of the potential energy of the hydrogen and oxygen has been converted to heat. If the water molecules had the same amount of energy, it wouldn't be giving off this heat. If it had more energy, then it would have absorbed heat. Heat would be one of the reactants and not one of the products. So because it's a product, you know that the energy has been given off by the molecules. It has to have come from somewhere. And the takeaway from this is that you can measure a lot about the system that you wouldn't necessarily have thought you could by controlling the system carefully and paying attention to what it's doing at any given moment, by paying attention to various state functions. And that actually is the first law of thermodynamics, that delta U equals UF minus UI. It's another statement of conservation of energy. Now, that's not to say this is the only way to state the first law in mathematical terms. You can state it in a bunch of different ways, and people do, depending upon the situation. So, a less mathy way of putting the first law is that energy can neither be created nor destroyed. If it comes from one place, it has to go to another. If it goes one place, it has to come from somewhere. Now, go back to an earlier part of the first lecture. You'll recall that the system is the thing under consideration. The surroundings are literally everything else. So system plus surroundings equals the entire universe. So the internal energy of the universe absolutely cannot be measured any more than a system or surroundings could be, but it's equal to, it has to be, the internal energy of the system plus the internal energy of the surroundings. That's the great thing about state functions. Now, another thing to consider is that the total energy of the universe has to be constant. Okay? There's nowhere for the energy to go, there's nowhere for the energy to come from, so the change in internal energy of the universe is going to be 0. And the change in the internal energy of the universe is going to be equal to the change of the system plus the change of the surroundings, or change in internal energy of the system is equal to the negative of the change in internal energy of the surroundings. Pay attention to those negative signs. They will bite you in the keister. All right. Just remember, system, surroundings, equal magnitude, opposite signs. Don't lose track of those negative signs. So, for example, if you have a system and the change in internal energy of the system is equal to 5 joules, it has gained 5 joules of energy, so that means the surroundings must have lost 5 joules of energy, so negative 5 joules. And that sort of thing is going to come up over and over again with energy moving from one place to another. You're going to hate, well, me mostly, but you're going to hate the problems too as you try and keep track of where energy is coming from, where it's going to, and that goddamn negative sign. Now we need to talk about work and heat, and as they're understood by physics. Because you can't talk about internal energy without talking about work and heat. So let's say you have a system that is completely isolated from everything around it. No matter can get in or out. No energy can get in or out. And if the system is completely isolated in this way, that means that the change in internal energy for the system has to be equal to zero. Nothing in, nothing out. It's isolated. So that means that if somehow, some way, you put heat into the system, that means you have to get work out so that delta U will remain zero. Well, all right. So you have a pretty good handle on heat, sort of. I mean, if nothing else, you've probably been burned by stuff before, but what the hell is work? What is work in the physics sense of the term? What does it mean when we're talking about work here? So for this, it would help to remember that thermodynamics was first developed, invented, discovered by people who wanted to make steam engines work as well as they could. So here we have a cylinder, where gas will expand. Here you have a piston, and the gas will push on the piston. That's the basics of a steam engine. You put heat into the system, the gas expands, it pushes on the piston, and does work. That's why they were studying this. That's what they were hoping to accomplish. The bestest steam engine ever. So what they were always trying to do was to strip it down to the bare essentials, boil it down. And so for this system, delta U of the system is equal to 0, and it's equal to Q plus W. The heat in and the work out should add up to 0. Now, if you've taken any physics classes that have talked about work and heat in terms of systems and surroundings, you're going to be a little bit annoyed over the next few weeks because chemists and physicists do things a little bit differently. Physicists have it ass backwards. They're stupid and I hate them. We think about things in terms of the system. So heat into the system is positive. It's greater than 0. The system is getting warmer. Heat out of the system is getting colder. For the work, it's kind of the same thing. If you get work being done by the system on the surroundings, then it's less than 0. The system is expending energy to do that work. If work is being done on the system by the surroundings, then the energy is greater than 0. The change is greater than 0 because the energy or the system is receiving the work done by the surroundings. Now let's go ahead and try and put this in somewhat more concrete terms. When the piston here is expanding, the system is doing work. It has to push against the surroundings in order to get that piston to go out. On the other hand, when the piston is going in, it's the opposite. So if the volume of the system, capital V, let's make it pointy, if the volume of the system is increasing, then delta V is greater than 0, then the system is doing work on the surroundings. It's pushing out against everything that's outside of it. So the reason it's able to expand is because pressure inside is greater than the pressure outside, and it's able to push. But it's still encountering resistance, and so on. Okay? So pushing outward against the surroundings means doing work, means that pressure times change in volume is going to be the work that you're looking at. Okay? Liters times atmospheres is technically a measure of energy. You manipulate the units correctly, you're going to get joules. Okay? So P delta V is a measure of energy. It's a measure of the work that you're doing. But we also need it to be in the correct sign. Okay? Because if P, pressure is always going to be positive, and if the final volume is greater than the initial volume, the system is expanding, it's doing work, then delta V is also going to be greater than 0. So we need, however, for work to have a negative sign when the cylinder is expanding, which means that work is going to be less than 0, and if P delta V is greater than 0, then we're going to need to throw a negative sign in there for everything to work out for us. No pun intended. Okay. So what that means is when all is said and done, for chemists, work has to be equal to negative P delta V. We have to have a negative sign in there in order for this to work out in our favor. Work equals negative P delta V. Just to reiterate, this is one of those super mega important equations. You're going to want to remember it. Now, for the less mathically inclined among you, when the system is getting worked on, it's being compressed, it's being squeezed by the surroundings. You have to work really hard to squeeze things, right? Whereas, on the other hand, when you spread out, you relax, you expand, you take up more space, you're more comfy, everything's really awesome like that. So when the system is expanding, it's losing energy, it's relaxing, it's letting go. But when it's being compressed, it's being squeezed. The work is being done on it, and energy is going in. You're getting more tense. Okay, so less volume means positive work. Greater volume means a negative work. Now, how do we go about measuring Q and W? Q is actually fairly straightforward. It's the laboratory technique known as calorimetry. You just measure the change in temperature, and you relate that to the substances involved, and that can tell you about heat. Work is often measured in terms of volume change, such as steam engines, but not always. Sometimes it's for example, chemical work or electrical work. Like a battery releasing its charge in order to power a fan or a clock or something. So there are a lot of different ways to measure both of these. It depends on what system you're looking at, really. You either have to be able to figure out what these two terms are, or how to calculate them, or I should say, you have to be told what they are, or you have to be able to eliminate them so that they just can't occur. You isolate the system, or you make it so the temperature can't change, or so it can't do work, things like that. But we are going to go ahead and leave it there for now. When we come back in the next lecture, we'll move on and continue discussing thermodynamics.